2-5, day 2. Get that labeled over here. Here's day 2. Exact same goals as day number 1. Okay. Exact same goals. We're finding zeros. That's the name of the game. Again, a graphing calculator that gives you the ability to quickly put together a table of solution points is going to be helpful, particularly on example 4. It's just, you know, ultimately to get a 0, we gotta pick an x value and then verify it with synthetic division. And again, the only purpose of that table is to just, as far as checking the right cases, that's going to give us a heads up on which ones to do. Okay, we've got ourselves a cubic, which means we're looking for 3. Okay, 3 zeros total. Now, just for the sake of space, I'm not going to list out all the rational zeros. It's all the factors of 12 over all the factors of 10. I think there's like 26 different possibilities. It's like 1, 2, 3, 4, 6, 12, plus, and this is all plus or minus. 3 halves, 1 fifth, 2 fifths, 3 fifths, 4 fifths, 6 fifths, 12 fifths. There's a lot of possibilities. Okay? And I'm not even going to look at all of them. But that would give you the possibilities that you should be checking. Now, the one thing this would give you a really big heads up on is when you go to your table, it would tell you like what fractions you need to look at. Okay, all those ones that I were listing that were like over 2 or over 5, those should be values that you check because it's possible. That's the whole point of the list. It's possible there's rational zeros at those particular values. Now you'll see from that list, okay, and again, for the sake of space, I'm not going to list it out. From the rational zero test, you would see x equals 2 from your table. Okay, that is the only one that would show up. Okay, so now, and remember our kind of philosophy on the different types of zeros, rational, irrational, and imaginary. We always have to find all the rational zeros. We have negative 10, 15, here's 16, and negative 12. Okay. Numbers are a little bit bigger here, but still the same process. Here we get negative 10, positive 6, 2 times 6 is 12, and there we go. So we have one of them. Okay, again, we go to the table, we'd see 2, we verify it with synthetic division, 1 down, 2 to go. Okay? Now we get to an interesting point because you would look at your table and see that you could look through that whole list of all, I think, 26 possible rational zeros, and you would see there are no more. You found the only one, which means a couple of different things, a couple different possibilities. Imaginary zeros always come in pairs. Okay, so it's possible at this point that maybe we have 2 imaginary zeros, or they're real zeros and they're just irrational. You could actually look at the table and see. If you see that at those, like there's 2 other possibilities in the table where the graph is changing sign, where it's actually crossing the x-axis, that would be a little hint that, hey, wait a minute, they're irrational. Okay, imaginary zeros won't show up in the table like that. Okay? Now, it is a case, because we have said, sometimes we expect to find those last two. Sometimes we don't. It all depends on what we have left here. Did we get our polynomial reduced down to a quadratic? It was a cubic. We did one round of synthetic division. And as a matter of fact, we did. Okay, we got it reduced down to a quadratic. And again, anytime we see this case, we're expecting to get the last two. Okay, you could try to factor. Don't. It's not going to go well, right? Because factoring, it works out really nicely if the zeros are whole numbers. Kind of nice if they're fractions. Irrational and imaginary don't. But we have this tool of the quadratic formula, right? And you can always go to that, which is why I always expect you to find these last two. So I've identified A, B, and C. I'm just getting them all plugged in where they go. All of this is over 2 times A. And this whole process in section 5, it's probably a good idea to keep the quadratic formula handy. You just come back to it enough. Don't worry about memorizing it. You should put it on your note card for a test. Now, as I simplify this, I want to show you something. Because it's still, at this point, the issue may still be in doubt as to, are we talking about 2 imaginary zeros, or are they both irrational? And before we get all the way to the end, there is a way to tell. We get to this point, and I can tell. I look at the square root and what's underneath. Okay, fancy term for that number is called a discriminant. You don't need to know that, but that's what it's called. If it's positive, like this case, it's 265, you're talking about irrational zeros. Okay? The graph does cross the x-axis at 2 other occasions. They're just not very nice numbers. Numbers like this. And these are just approximations. And if we find irrational zeros, that's the approach we're going to take, is we're just going to go to decimals and give them as approximations. We could be fancy and simplify the line before and give them as exact, but if you wanted to, in fact, on a test, I'd give you extra credit if you put them as exact. I would take the decimals, 1.063 and 0.5639. Okay, again, those are they're numbers where the graph actually crosses the x-axis. Our table in synthetic division didn't find those because they're irrational. Okay, there's no way to write those numbers as fractions, and the big list that we would get are all fractions or whole numbers. Okay, but 2, negative 1.06, 0.56, we've got all 3. Okay, but keep in mind on that case we got it reduced to a quadratic, so I do expect that you'll find those last 2 irrational zeros. Okay. All right, here's a great one to see. This is probably the best example you're going to have. It's got a lot of stuff going on, okay? You'd start with the rational zero test. Here I'll list them out just to kind of reinforce that whole idea. You start with the constant at the end. Listing off factors of 8. There's not too many. 1, 2, 4, and 8. The lead coefficient is 1, so this is over plus or minus 1. Okay. And that doesn't add any new factors. Okay. And again, what I really like about this is it tells you a little something before you go to your table. As far as changing the x values to get fractions, we don't need to. Okay. I need to look at plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. Okay? If this graph has rational zeros, there's no guarantee there's going to be 5, because that's at most what I'm looking for. That is where they are, right? If we were to check all those and we would see that it didn't have any, which is not going to happen, there's no other possibilities we have to worry about checking. Okay. Now I would go to my table and I'm going to put over here just to kind of get started with our list. I would see 2 of them. I would see 1 and I would see negative 2. Okay? Now the order that I do this doesn't really matter, but it's time to go do some synthetic division. Now I'd have 1. Don't forget the 4th power is a 0. 1, 2, negative 12, and 8. A lot of terms on this one. This is a 5th degree. All right? This is kind of getting out there. We've seen, I think in day 1 I showed you a 4, right? This whole process is starting if we have at least degree 3, but here's our first look at a 5th. I bring down the 1. One times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. 1 plus 1 is 2. There we would get 4. And there we go. 1 is a 0. Okay, now very, very important, right? Because we're still not completely sure at this point in time if we're going to be able to find all 5. Because we looked at the rational, well, yeah, we know they're not all rational, right? Because, you know, we only found 2. And we know from our rational zero test, we found the only 2 that this has, okay? So, you know, we'll kind of wait and see here. There's something going on with the other 3. In the meantime, I'm just going to go ahead and verify the second one, but I don't want to go back and start over because, again, my goal here is to take this 5th degree polynomial and we're going to reduce to a quadratic. After I do the first round of synthetic division, I have it down to a 4th degree. I'm about to do another round to get it reduced. I'll get a bunch of coefficients right here that are 3rd degree. We're going to have a 4, negative 8, negative 4, 8, and 0. Okay? Now this is where this problem gets really tricky. And it's a great one to see because I really couldn't give you one on a test that's trickier than this one. This is about as far as I'd go. Now I did give you a hint in the instructions that as far as the remaining zeros, 2 of them, you know, conjugate pairs, that's what the imaginary zeros. 2 of them are imaginary, okay? 2 of them are imaginary. And that's fine as long as we get it reduced to a quadratic. We could use the quadratic formula, and even if they're imaginary, that's going to take care of itself. We'll get the whole negative square root, and we're good. Except we don't have it down to a quadratic yet. We have it down to a cubic, and as far as like not just doing synthetic division and checking zeros, we don't have any other options if we're dealing with a cubic, and we're out of zeros to check. Or are we? We're really not. Okay? This isn't to scale to this situation, right? But this is, if you found yourself in this situation, here's what you should do. Okay? Again, this is not, I'm not drawing the cubic, or the 5th degree that's there. There are 2 types of zeros that we have talked about. One at the x-axis that crosses, and the other one where it bounces. Okay? It could be, no guarantees, okay? it could be that this is one of those cases where these two rational zeros that we found, that one of them is what we call a bouncer. Okay, it just came down and touched the axis and then bounced off and went back the other way. Now, if you looked at your table and looked really closely, you could see, all right, at -2, like any other crosser, you will see a sign change, that the y values go from positive to negative. If you're dealing with a bouncer, as you look on either side of the zero, you won't see a sign change, because that's what's happening. The y values are positive, it touches the axis, and then it goes back up. Okay? That is exactly what's going on here. And if you get stuck like that, you may need to check one of those two zeros. Okay? When we were factoring, this was the concept of a factor that was a double. Like it had 2 of that factor, or we said its multiplicity was 2. Okay? Right now what it means is with this whole synthetic division process is that we can do it again. And look what happens if we do it with 1, we get a 0 again. Now that just counts as like, well, it sort of counts as like 2, because now we found 2 rational zeros, but it's like we verified 3, and what it means now is we're looking for 2 more, but we look down at the bottom and go back to a polynomial here. And we have a quadratic, okay? A is 1, B is 0, C is 4. If you want to plug that in the quadratic formula, be my guest. You certainly could. I want to show you a different way. Right, we'll get the same answers, and if you're just like, don't show me a different way, I just want to put it in the quadratic formula, totally fine. That'll never fail you. That'll always work. This one, you can take a slightly more efficient approach because it doesn't have a term for B. So I can just move the constant term to the other side. Now I'm just solving. I take a square root, and I get plus or minus the square root of -4. This is why we're going to get a conjugate pair. Square root of 4 is 2. Put in the I, and there we go. Plus or minus 2i. Okay. We only got 4, but remember we verified the 0 twice, so it's really like we have 5. That's all of them. Okay, that's every possible 0. That's a great example. It's 5th degree. It's got 2 imaginary zeros. It's a case where you can find them with the quadratic formula. It has a 0 that's a bouncer that you have to verify twice with synthetic division. Before a test, that's a great example to study. But everything that I could throw at you on a problem to find zeros is in there. And let's wrap up day 2 with a word problem. Okay, it's obviously going to involve finding zeros. It's not just, we don't just find them for the sake of making a graph. They come up in other cases. Okay. Now, I did tell you if we're doing a word problem, you are free to not worry about imaginary zeros. We don't need those. This is going to involve finding a real zero, and most likely is going to involve finding a rational zero. Okay, so here's the situation with the problem. We're making these kind of fun-shaped pyramid candles. They're kind of cool. We're figuring out the dimensions. There's the height. It does tell us that the base has to be a square. Okay. The other thing it tells us here is that the height has to be very specific. If I am calling the sides of the base x, the height has to be x minus 2. It's got to be 2 inches shorter. So if my base was 10 by 10, okay, the height would have to be 8. Now just look at the diagram and think if you put in those numbers. Right? If x is 10 by 10, you put in 10 for x minus 2, the height would be 8. Okay? Now what's preventing me from doing that is I have to check and see, do I have enough wax to make that candle, a 10 by 10 by 8? Just from crunching the numbers, and actually we need a formula to crunch some numbers here. This would be given if this would have been a test question. Pyramid is a third base times height. Okay? And if I plug those numbers in, and I would see that I think 10 by 10 by 8 is too big. I mean, that would be a huge candle. But I don't have that much wax. I only have 25 cubic inches. All right, so here's what we do. And you'll kind of see it step by step, because at this point it's a little weird. It's like, okay, you're looking at a volume problem, but we were finding zeros of polynomials, and how are we going to do that here? Well, take the formula that we had. I'm looking at the volume formula. I just put in 25 for v, because v can't exceed 25. A third is a constant. That's not going to change. The base, all right, I don't want to call that b anymore. It's a square that's x by x. So if I'm talking about the area of that base, I would rather call it x squared, because now I'm in terms of the dimensions of the base, and that's what I want to work towards. Like, what value should x be? All right? And for h, I don't want to work with multiple variables, which is why I did the work earlier to define that as x minus 2. Starting to look like a polynomial, isn't it? Okay? Now, essentially what this problem becomes is we have to solve that. Okay? When you're solving an equation that involves a polynomial, okay, it really turns into finding zeros. At the moment, it kind of looks like a quadratic, but I distribute x squared over x minus 2, and it becomes 1/3 x cubed minus 2/3 x squared. And we see it's actually a cubic. Okay. Now, it's a volume problem, and volume always includes 3 dimensions: length, width, and height. Any application problems we do, you will see, and I mean, you should think of that, right? 3 dimensions means third degree polynomial. Okay, so as you practice with more, like this one you'd have no expectation, but on others where you do, you should see this problem and think cubic. Volume problem means it's going to use a cubic. All right, the next thing I'm going to do is kind of a weird step, but I really don't want to deal with these fractions. And at this point, I couldn't ask you to do that because I haven't give you any, that have, those coefficients. The numbers in front of the x variables, we haven't seen any that were fractions. So you can assume if you see them, I'm going to give you a way to get rid of them. Like right here, if you multiply both sides by 3, left side becomes 75. The 1/3 just becomes a 1. The 2/3 just becomes a 2. And now this equation is starting to look a lot more like what we saw in the previous 5 examples. Okay? I take one more step right here and move the 75, and I have x to the 3rd minus 2x squared minus 75. Now it looks exactly like all the other problems. Okay? And I have that equation, and I need to find a 0. Okay? Now there's 3 of them. All right? If there are any imaginary ones, I don't really care. I'm pretty convinced here I'm looking for a rational 0. Okay? All the factors of 75 over all the factors of 1. Now use some common sense with an application. I could check plus or minus 1, plus or minus 3, plus or minus 5. None of the negatives apply, right? I'm expecting a positive answer, so get rid of all those negatives. 1 seems like a possibility. 3 is a real possibility. 5 is a real possibility. Once I get past there, then we jump up to 25. Like 15 and 25 are also possibilities, and you can check those in the table. My gut says those are too big, right? Well, look at 25. If the whole volume can be 25 cubic inches, I don't think the base can be 25 by 25. Okay, nor could it be 15 by 15. All right. Now you go to your table, and you're going to find x equals 5. Now don't forget, You found it from the table. We really shouldn't have. We should have just gone to check the cases with synthetic division. Okay, that step still needs to be in this problem. Kind of a formality. I mean, it's important to do, but we know it's going to work. Okay. X is 5 inches. Now I got to finish by answering the question, which is about h. Okay. Simple jump to get to h. If I said the base was going to be 5 by 5, my relationship to the height that it got to be 3. Now here's the cool thing. You can go back to your volume formula, which we had up here. You could plug in, 25 for the base and 3 for the height. Like, you can crunch those numbers. Remember, we had 25 cubic inches of wax to work with. You can go plug them in, but from the work we did with the polynomial, it's going to work, right? We've got dimensions that fit the criteria that were described, and we know that it's going to use the exact amount of wax that we had, 25 cubic inches, no more and no less.